Okay, so to finish off the circle notes, we're going to have a look at a few more questions that use circle theorems. So the first one we've got here, we've got points A, B and C, which lie on the outside of a circle, and the question is that we want to prove AB as a diameter and hence find the equation of the circle. Now, if AB was a diameter, let's make some assumptions here, then what would actually be true? What is the thing that this is actually asking us to use? Well, if we were to complete this as a triangle, then this would be the semicircle right angle theorem, i.e. this would have to be a right angle here. And that works both ways. If this is a right angle, then that has to be a diameter. So what we're going to have to do is look at the gradients of the lines AC and BC, and that will be enough. If we can show that they are negative reciprocals of each other, if we can show that they're at right angles, then we can show that that's a diameter. Those are the two equivalent statements. So we're going to find the gradient of AC, and we're going to find the gradient of CB as well. So for AC, it's going to be, let's say, 9 take away 1, and minus 4 take away minus 8, so plus 8. Make sure you keep those the right way around. That will give me 8 over 4, which would give me a gradient of 2, and that looks about right from the diagram. It's definitely positive, definitely quite steep. And then we want to find the gradient of CB. So do the same thing. So let's do B first. So 5 take 9 and 4 plus 4, because again let's take away minus 4 there. Minus 4 over 8 is minus a half. Okay, cool. So we basically got what we need. We now need to state that we've got what we need. So we could say that the gradient of AC is the negative reciprocal of the gradient of CB. So that's pointing out what we've shown. And that would mean, therefore, that ACB is equal to 90 degrees, and therefore AB is a diameter. And you could say why, because we have right angles in a semicircle. That last bit is always a bit fiddly to sort of put together, but that's what we're trying to say. It says, hence we want to find the equation of the circle. So how are we going to use what we've just done there to find the equation of the circle? Well, if we want the equation of the circle, we need the equation of the centre. And let's call that M, because it is the middle of A and B, isn't it? If they're a diameter, then that's a radius on either side. So we'll find the midpoint of AB. Remember, we do that just by adding up the 2 points and halving it. So for the x-coordinate, 4 plus minus 8 over 2, and for the y-coordinate, 5 plus 1 over 2. So that'll give us minus 4 over 2 and 6 over 2. So that will give us a centre of minus 2, 3. And then we also want to find the radius. So we could either find the distance from A to B and halve it, or we could find the distance from M to B and not have to halve it. Now, as the second of those options requires less work, I'm going to do that. So we'll find the distance from M to B, and that's going to be a Pythagoras. So B was 4, 5, wasn't it? Yes, it was. So we want to do difference in x squared, so 4 minus minus 2, and the difference in y squared, so 5 take 3. Okay, so that's 6 squared and 2 squared, which is overall square root of 40. So we now have a centre of a circle, which is minus 2, 3, and we have the radius of the circle. So that was our centre, this is our radius. So we can put this all into the equation of a circle, which would be x plus 2 all squared, because the centre is at minus 2, plus y minus 3 all squared, because the other centre is at 3, and then that's equal to r squared, so root 40 squared would just be 40. And we're done. So you can again see that the sketch makes this question doable. If you don't sketch it out, you're really going to struggle to understand what's going on with it. Let's bear that in mind on our last example here. Let's just change that, let's just say on. So we've got P, Q and R, which all lie on the circumference of a circle. Now, I'm going to try and vaguely sketch this as best I can. So we've got 3, 16, we've got 11, 12, and we've got minus 7, 6, which will be to the left and lower than either of them. And looking at that, it looks to me like your circle's going to look something like that. It says the perpendicular bisector of PQ. Okay, so that was our P, that was our Q, that was our R. So let's just add this on, shall we? So what do we mean by a perpendicular bisector? We mean if we were to draw a line from P to Q, then the line that meets it at right angles and splits it exactly in two. That would be y equals 2x. Okay? And we want to find the perpendicular bisector of PR. So that's going to be the line that cuts that exactly in two. Now there is a fact that we're going to use with that in a second, but actually A doesn't require us to use the sketch yet, because all A wants us to do is to find the perpendicular bisector, and well, we know the coordinates of P and R, so we can find its midpoint, we can find its gradient, and we can turn that around. So let's do that. So we'll find the midpoint of PQ, of PR rather, which would be 3 minus 7 over 2 for the x coordinate, and 6 plus 16 over 2 for the y coordinates. That's minus 2, 11. And we also want to find the gradient of PR, which is going to be, let's do P first actually. So 16 takes 6 for the y's, and 3 plus 7 for the x's. So that would be 10 over 10, which is nice, which is 1. And so the gradient of the perpendicular bisector would be equal to the negative reciprocal of that, would be equal to minus 1 because it's perpendicular, and it will go through this point, minus 211. So to find our actual equation, we can put all that together, and we can say, okay, so y minus 11, because we're going to use this midpoint, is equal to minus 1, because we're using this gradient, x plus 2. So y minus 11 is minus x minus 2. Let's move the 11 across, it's equal to minus x plus 9. Cool. Okay, so then we're actually going to use our diagram, because it says we want to find the centre of the circle, and the circle theorem that's relevant to us here is that the perpendicular bisector of a chord is a diameter. So let's write that down. The perpendicular bisector of a chord, which is what PQ is and what RP is a diameter. And if this red line is a diameter, and if this green line is a diameter, then they both must meet at the centre of the circle. So this point here must be the centre of the circle. And we found that this was y equals minus x plus 9. So all we have to do then is solve this as like an equation. We've got y equals 2x and we've got y equals minus x plus 9. So all we need to do is to find the intersection point, which would be equal to the centre of the circle. So easy way of doing that is just sub in that y equals 2x. So 2x equals minus x plus 9, 3x equals 9, x equals 3, and then we know y equals 2x, so y equals 6. So our centre of our circle is 3, 6. Cool. And then the last question is we want to find the circle's equation. Now we're basically there, aren't we? We've got the centre of the circle already, that's 3, 6. We don't have its radius, but we could find the radius in loads of ways because that's just the distance from the centre to R or to P or to Q. So we'll find the distance CQ, why not, which is going to be, so if C is 3, 6, and that's 11, 12, so it's going to be 12 take away 6 for the Y's, and it's going to be 11 take away 3 for the X's, which would give us 6 squared and 8 squared. It's going to be our old friend, the Pythagoras triple, that one. 36 and 64 is 100. So the distance CQ is 10, and that is the radius of our circle, because it was the distance from the centre to the outside. And as said before, this is our centre. So if we want to find the equation of the circle, well, we've now got everything we need. X minus 3 all squared plus y minus 6 all squared equals the radius squared, equals 100. Job done. Again, really important point here, sketch it and all will become clear. Cheers.